Okay, we're moving on now with three speakers. We have Dennis Neer from Siemens Industry Software, Alexander Wirsch from the Technical University of Würzburg-Schweinfurt, and Dominic Sippel from EOS. They're going to be talking about how additive manufacturing is transforming robotics and automation. So they're showcasing AI-driven design, CO2 tracking, and digital twin simulations for lightweight grippers, as you can see on stage there. And how they can offer sustainable and efficient solutions in modern industrial challenges. So, gents, over to you.
Thank you very much, and a very warm welcome. So, we want to talk about how we can change with additive manufacturing, robotic industry and gripper industry, and make it ready for the industry. And for this, we come today with three people. From EOS, Mr. Dominic Sippel. From the Technical University of Schweinfurt, Mr. Alexander Wirsch. And from Siemens, it's me, Dennis Neer. Good. I need to switch. Perfect. So, why we have a project Bionic Grippers and what it is? Maybe this example. This is a gripper for battery manufacturing. You use it in automotive factories. He grips a battery module with a weight of 25 kilograms. And the original gripper is a very, very heavy gripper. Normally, we should have a video. Here we go. So this is the way normal grippers look like, made from aluminum, from big plates, standard parts or profiles, and they're very heavy. This original one, for example, or original gripper for this one has a weight of 50 kilograms. And we show how we can do it with software to optimize it, to make a topology optimization. Then we printed it. We changed the material from metal to polymer, and so we come down from 50 kilograms to 2 kilograms. And this is I think a very good use case to show our customers how additive manufacturing bring a lot of values to them. So it's about weight saving, material change, cost reduction, everything inside. You can save a lot of energy when you use a lightweight gripper on your robot, and even the cycle time will be reduced. So benefits, benefits, benefits. Good. So today we take you on a small journey from the design. This will be the Siemens part with Siemens software. Then we hand over to EOS, how we manufacture this little wonder of industry. And then we hand over to the Technical University, who will test it in real life with physical tests. So we really combine the digital idea, the digital designed world, with the real life to make it industry proof. Good. But again, back to the use case, to the gripper. Normally, when we make a comparison with nature, when we look at an ant can carry 70 times of its weight. When we look into the industry, where we use our industry robots with the grippers, with pneumatic, with electrical actuators, we manage as humans that our cool designs and robot grippers can carry 0.004 times its weight. So really lose against nature. To change this a little bit, to be more effective, we come to the lightweight design. And what will be the impact on why we do it? Normally, when we carry a battery module, this is some of these modules this gripper will carry, has a weight of 25 kilograms. For this, normally we need a gripper made from metal, around about 50 kilograms. To carry all this stuff, we need a big robot, over 1 ton, and this robot emits nearly 6 tons of carbon dioxide every year to carry all this stuff. And there are more than 3 million robots out there, so a lot of carbon dioxide we emit. Can be better. So what we can do, we can take the gripper out of this calculation and hope that for the downstream process, it has a lot of effects, energy savings, maybe using smaller robots. And when you remember, this new gripper has a weight of 2 kilograms, so really erased this big weight out of this calculation. Some facts, so we go from 47 kilograms to 2 kilograms. Also interesting, to manufacture such a gripper, we emit nearly 700 kilograms carbon dioxide with this milling for the raw materials, with this metal stuff, everything very, very high emissions. And when we printed it with EOS technology, carbon dioxide reduced materials, we go down to only 30 kilograms of carbon dioxide emissions for this gripper to be manufactured. So the first big benefit starts already in the manufacturing of the gripper itself. And so this is a very fair number here. Normally when the users, customers ordered grippers the classical way, they need months to get it. 3-4 months, no problem. When we print it, it's your own printer, it's free, you have it next day. When you ordered external suppliers, a week, 2 weeks, so we are really fast to produce it. And it's really cheaper. This grippers cost some 10,000 euros. Here we talk about 1,000, so also another value. Endless values. So now we go into the factory itself. When we now use our Siemens software, the design we make with Siemens NX and topology optimization, wonderful software, and we also can simulate the whole plant, the robot cells, the whole factories, and there we simulated the old setup. A big robot with the old original gripper, with the battery module. We can measure real lifetime, how much energy we need for it. And then we simulate what will happen when we take this lightweight gripper, created by this beautiful EOS technology, designed with NX from Siemens. And then we find out, okay, this lighter setup needs a smaller robot. We don't need this big one anymore. And this means we save a lot of energy. More than half of the energy can be saved. This means also 3 tons of carbon dioxide less every year. And 50% less space, because the robot is smaller, so you have more space for logistic area, or you can your sites even more effective. And at the moment, the best benefit for our customers, it's this 20% cycle time reduction. So with this cheaper, lighter, nice-looking solution, we can produce 20% more parts. The factories can produce more goods, sell it to the customers, so a real booster for the industrialization. Good. A little bit the process, how we do it together with EOS. We take a use case, we find a nice one, then we go to NX, make the design of the lightweight body here, ready for the correct material. So in this case, we take the material properties from EOS, set it up in our topology optimization, and this part exactly fits to this material for this use case and load cases. If you have another battery, other weight, other material, just to change a parameter, press update, you get a new gripper. By the way, we have a cool app. You designed it once, then with the app, some sliders, other weight, other length, whoop, waiting 5 minutes, you have your new gripper for this new use case. It's good. Good. After the optimization, we already have a simulation. We know where are the stresses, where are the maximum deformation, so it's a real digital validation of the product. Later, Professor Försch will validate it in the real world with physical tests, and we compare. Then we go to the build job preparation, we put 4 grippers in one shot into the build chamber, and then the magic of EOS will start with their printers to produce it. So, and I think now I will hand over to Dominik Sippel. Please.
Thank you so much, Dennis, for this presentation. I'm Dominik, and before we hitting the print button, I like to just quickly recap. And so, who of you is using CAD, actually? It's okay. Not many, 10%, 50%, but what you do actually with CAD, you have a sketch, you extrude, put another sketch there, revolve, put another sketch there, and then cut. And by doing this feature by feature, you're creating the part which is supposed then to have the requirements, what you need, right? And this approach is completely different because you set up the constraints and the force. And by having this, it is automatically, by simulation, it's creating the design for you. And why we're doing this? We're doing this before right now it's metal. We like to do this with polymers. So the designer needs to have confidence. He needs to have evidence that this is working actually, right? And this is why we need a simulation. Okay? And this is what we have 2 challenges as a printing company right now. We need to provide the data that the simulation is working. And our second challenge is that we can produce it in a way that we have the data in a consistent, repeatable, and reproducible way. So these are the 2 challenges we do have. And maybe we can, we are EOS, we are 35 years in the market. We also do metal printing. So I think metal is one step beyond with medical, with aerospace, first flying parts, A320 Neo, and space industry. And we like to bring this experience also to polymer industrial application. This is what we like to do. And a quick glimpse, so I take advantage right now. This is the machine we launched on this Formnext. We have several machines in our portfolio which are capable to build this part, P3, P5, P7 on an industrial scale. And then it's not only a system. I don't like to show you a system. We need to have the material which is qualified, the system, the process, but you need to have you have 5,000 machines in the market, so you need a service organization that in an industrial environment, the service can have the uptime on the shop floor, as well as application engineers who can implement and ramp up such application at customer side and support this. So this is a lot more than just hitting the print button, obviously, but I try to emphasize on that. So here's a quick glimpse about some attributes we like to share. Obviously, it can be colored. It's a PA2200. It's the most used material in the market. We do have better reuse materials at the moment, like with 70, 80%. Right now, we're starting with the 50% because we can also provide certificates for biocompatibility, and also we are the only company who has certificates for food contact. Mechanical properties, like I said, we need to share the material data to the software so it can come up with a solution which is fulfilling the requirements. These are values, dry values from tensile bars. What we do need is actually, because PA12 absorbs water, so it changes its behavior. Elongation of break usually goes up, tensor strength, E modulus goes down. So we need condition values to make sure that the software and the simulation is working properly. And last thing I like to tell is this is the building frame from our P3. We have a nesting density of 10%. Like I said, we can also go to 70, 80%, and then having a very good ratio or almost zero waste in our system. And by saying this, I want to hand over to Professor Wersch, who will then orchestrate a lot of testings to make sure that this part will be a validated part for industrial environment.
Thank you, for Mr. Sippel. Okay, why I'm standing here today? First, I'm happy to be here today and to be able to contribute to this project, because I think this is an important project. My journey in the field of designing lightweight grippers and doing it with Siemens NX and bionic design started 5 years ago when I was working for industrial partner developing a new robot handling or new handling system for a robot. And the statement of my partner was that in each system, the gripper solution takes more than 50% of the total payload of the robot. And I thought, this cannot be possible. And this was a starting point of my project. The project I talked about, this high weight of the gripper, which was designed 5 years ago for industrial solution, had really a great impact on the whole solution. We needed a bigger robot, bigger machine access, 10,000s of euros more costs. Not talking about the costs, daily costs when the system runs in production. And so, in my position as a professor at university, I started with several student teams and developed different solutions. So the students had to do a bionic design of the gripper. Usually teams of 2 or 3 students. This is the result. This is running at a robot. And also they did the same work. You saw what was introduced from Mr. Sippel. From Mr. Nier. Sorry. Okay. And then, after having the plastic part, we produced it in metal. Same solution in metal. And I have for systems. This is a parallel gripper redesign from a very well-known German gripper manufacturer. I say it's a Mercedes from the gripper manufacturer. And when he was here at my university, we run this gripper on the robot. And then we discussed about tolerances. And this was a starting point. First point is, are these grippers ready for industrial use? Because they talked about some tolerances which were not okay in this first prototype. But then I decided to go further, and we invested in measuring technology, robots, and we will make the proof that these systems are ready for the industrial use. The concepts you see here, even the metal gripper, the man here is handling this gripper with one hand. The original gripper was more than 10, 12 kilos. You will not be able to handle it with one hand. And here you see 2/3 of the material can be saved. And I have different solutions now and different projects. And we see only in metal, when we go in metal, we can already save 2/3 of the material and the weight. And if we get the step to do it with plastics, the impact will be much more. And this is what I want to show. We do not need a 60, 70 kilo robot payload with a 70 kilo payload robot to handle a 25 kilogram battery in industry. We do not need it. And we will do a long-term test. We will test the system. And as you can see, the robot, it is running in my lab. It is handling a battery with 25 kilograms. Payload of the robot is 30 kilogram total. So we are ready with our designs to go to industry. And what we have to do now is we have to make the proof that these systems have the readiness to be used in industry, because what we have to test is a long-term test. These grippers have to, let's say, make some million cycles without having wear. And this is a proof we will do. So we will do the testing of the mechanics. Static, dynamic, of course. We will test the wear when we have the gripper running in, out, millions of times. And we have a wear test rig, and we will test this system on our wear test rig. So we can see and prove that this system will run and will have no wear when we use it 1 million times. Also, we will take out a lot of information with our smart sensors and actuators we integrated and show what are the signals of the systems when the system is running in the long-term test. This is what we'll do the following month. So my work will start. Mr. Nier's work is done. Mr. Sibbel's work is also done. The work of both is well done. And now my work starts. And what I can say is, I will make a lot of mechanical tests. I'm looking a little bit to the time scale. Say static test, tensile test, bending test for the emergency stop, sharp impact test. And we will not only test this gripper, you can be sure I will destroy it more than one time. So I hope I will get new ones. We will do it in different stages, because a gripper does run not only 3 months, 5 months, it has to run 5 years, 10 years in industrial use. So we will also make artificial aging with our test rigs. We will do dynamic testing. There's one guy in the audience. He's the expert for dynamic testing coming from GM. So he got a lot of knowledge in this topic, and also he will help me with his knowledge. What we can say is, it's a team working together, and only in the team working we can get the results we want to prove that the system will work in real industrial use, that we are ready for industrial use. What I want to say is that today is for us a starting point for our documentation of this testing, and you can follow us on Gripper Thursday, and we will share you weekly our results with it. And there is a lot of cool stuff we are working on, and we will share our results because only if many people do see what is happening, we will get a confidence in our systems. Thank you for your time, and thank you, Mr. Sippel and Mr. Neer, for the chance to be with you here today and to start with this project.
Thank you. Great.
Thank you very much. If anybody has any questions now, I'm happy to pass out the microphone. If not, you can find out more on the Siemens booth. I know it's there. On the EOS booth, certainly there. And scan here and check out Gripper Thursday.
Gripper Thursday.
How many do you think you will destroy? How many are they going to need to make you?
How many will I destroy? I will destroy no one because my researchers will do it. Because without the help of specialists, we cannot get the results we want to have. But you can be sure, I think we will not destroy 5 total grippers. But 5 is a number that I have in mind. Perhaps some parts we will need 5 to 10 times. Of course, we also will need some samples and things for the testing. That does mean special probes we can use for our test rigs. This will we have additionally.
Well, at least they are cheaper, quicker, and more eco-friendly to manufacture after you've destroyed them, so that's okay.
Can I say one last word? This is the body of the gripper. Inside this body, there is a small smart servo gripper. And this small smart servo gripper does cost much more than the whole body. So it's really a cheap solution to get big grippers, because if you have to handle high masses, you do not have to buy a big gripper if you only have a small way. You can use a small one. And big grippers are very expensive. Here we're also talking about 5,000 to 10,000 euros, only such a parallel gripper that I showed you. And you see these grippers on millions of robots. So it is time to start with this project, because we can save every day millions of euros in production only when we change the gripper systems.
Perfect. Gents, thank you very much. Thank you. That takes us to a very short break, so we will be back at midday for the final 2 presentations of this day. But thank you very much for your presentation. Thank you.